Problem 19, Appendix B. In this one, we have this tube with the thickness, with a very small thickness. So this is a tube with the thickness of t, which is very small comparing to the radius. The way we show it, we usually use this symbol, which means thickness is much smaller than the radius, which is a. So if you revolve this thin circle with a very small thickness around this axis, it's going to make a tube. So if you look at it from the top, you're going to see a donut, right? But a hollow donut. And the question is, what is the mass moment of inertia about this axis? Let's call this axis OO. So what is IOO? This one is a little bit different than the previous one, than all the previous problems. It needs, you should be a little bit more creative to solve this problem. And the key point is what's going to be your integral element. Usually that's the most important thing in solving this type of problems. I would suggest to think about it at least for 10 minutes or so, and see the rest of the video. So to solve this problem, the integral element I'm going to choose is this, a tiny piece of this wall. So let's say this angle is d theta, and this angle is theta. So if you consider this element, which is revolved around this axis, so it's going to be something like this. If you look at it from the top, you're going to see a circle. So all of this together, a circle, is going to be a ring actually with this cross section, is going to be my element. So that's the element I'm going to use to solve this problem. So the mass of the element is dm, and if we have a ring, the mass moment of inertia of a ring about this axis, it's equal to the mass of the ring times the radius of it squared. Why? Because the distance of each particle, each piece of mass on this ring, let me show it here. If you consider any ring, the mass moment of inertia about the axis of it is going to be the mass of the ring times the radius squared. Why? Because each piece of this mass, they have the same distance. The distance of them is r from the axis, right? Based on definition of the mass moment of inertia, you need to multiply each mass to the distance of it from the axis squared, right? So this mass times r squared, this mass times r squared, all the pieces. So if you add all of them together, it's going to be the total mass times the radius squared. So going back to our problem, DIOO, which means the mass moment of inertia of this integral element, which is this ring about the OO axis, is going to be the mass of it, which is dm, times the radius of it, which is from here to here, the radius of the ring. What is the radius of the ring? Radius of the ring is going to be equal to, from here to here is r, capital R, and from here to here is going to be the radius of the circle, which is a, times cosine of theta. So plus a times cosine of theta. So if I put that here, mass times r squared, or dm times capital R plus a times cosine of theta squared. Now if I integrate this, which means I need to consider all the rings, I need to sweep this element all across this circle, and calculate the mass moment of inertia of all of those rings about OO and add them together. That's the meaning of integral, right? So if I take the integral from both sides of this equation, integral of di is I, and in the other side it's going to be integral of dm times r plus a times cosine of theta squared. But I cannot do this integral. I need to know what is dm. Mass of the spring, mass of the ring is going to be rho times the volume of it. And the volume is going to be this cross section times circumferences of the circle, right? So dm is going to be equal to rho times the area of the cross section is going to be the thickness. This is kind of a rectangle, right? It's very close to a rectangle because d theta is a very small number. It's a very small angle. It's going to be thickness t times the length of this arc, which is a times d theta, then multiply to the circumferences of that ring, which is 2 pi r. So it's going to be a times d theta times the thickness times 2 pi r, which is r plus a times cosine of theta. This is r, the radius of that ring. So if I put this here, then IOO is going to be equal to all of these parameters, they are constant. Let's write all of them together. 2 pi t a rho. Then we have r here and also r squared here. Together it's going to be r cubed times d theta. And we are integrating it over theta. To cover the whole volume, theta is going to go from 0 to 2 pi. So this is the integral that we need to do. And also, like the previous problem, we need to calculate m as well. So we need to integrate this one as well to find the total mass. Integral of dm is m, and integral of this side is going to be 2 pi t a rho times integral of r plus a times cosine of theta d theta, again from 0 to 2 pi. So we need to do this integral and also this one, then embed m in this guy. I'm going to let you to solve these two integrals, and I'm going to give you just the final solution. This one is very simple. Integral of cosine is going to be sine, right? So if you do this integral, this one is going to be 4 pi squared rho a r. And to do the other one, you need to expand this, r plus a cosine of theta to the power of 3 cubed. You need to expand this and also use you need to know that the integral of cosine of theta, this is simple. Integral of cosine of theta d theta from 0 to 2 pi. The integral of cosine is sine from 0 to pi is going to be 0 minus 0, so it's going to be 0. And in the same way, integral from 0 to 2 pi cosine cubed of theta d theta is going to be equal to 0. Why? I leave it for you, why this is equal to 0. And also when you are calculating integral of cosine squared of theta, which you are going to have it after expanding this, you need to know cosine squared of theta is equal to 1 plus cosine of 2 theta divided by 2 d theta. And you can do this integral. Anyhow, after using these equations, you can do this integral. Then at the end, you are going to get IOO is equal to 1/2 of m times 2 r squared plus 3 a squared.